Hey everyone, my name is Milecia McGregor, and I'm a developer advocate at Iterative.ai. And basically, we make these really cool MLOps tools that just make it easy for you to collaborate with other ML engineers on your experiments and to reproduce every training experiment you run. So I'm going to try to share my screen with y'all today. And I'm pretty sure you can see these slides. So today I'm going to talk to you about using reproducible experiments to make better models. And again, my name is Milecia McGregor, and I'm a developer advocate at Iterative.ai. You can follow me on Twitter at Flipped Coding because I talk about all kinds of fun data science and software stuff. Or if you want to get into the super nitty gritty details about ML ops, definitely make sure to hit up the team on Twitter at DVC.org. So just gonna jump right into it. I always like to start with just a quick overview of what I'll be talking about. That way you know which parts you really want to focus on. So I'll start with a little background on tuning hyperparameters because the focus of the talk today will be around tuning hyperparameters. Then we'll do some intro on using DVC and why you would care about this tool in the first place. And we'll go through an example of a grid search. We'll go through an example of a random search. And then finally, I'll wrap up with a few key takeaways, just some stuff that I really hope that you get out of the talk today. So first thing, little background on tuning hyperparameters. If you've been doing machine learning for any amount of time, you're probably really familiar with hyperparameter tuning. But basically, your hyperparameters are the parameters that define your model. So let's say, for example, you're working on some kind of crazy image classification project and you aren't sure what your learning rate should be, or maybe you want to play around with a neural net and you want to change the number of hidden layers you're working with, or maybe you change to a random forest classifier for some reason and you want to play around with the max depth on that. So these are the parameters we're talking about today. They're the ones that directly make your model. So without these parameters set, you don't really have a model yet. And the process of searching for these, for the ideal model is called hyperparameter tuning, or at least this is one portion of finding the ideal model. But what we're doing here is going through and trying a bunch of different values for these hyperparameters, and we're watching our model to see how it performs with these different updates. So maybe we have a learning rate of 0.5 and we want to change it to 300. I'm not sure why you would want to make that big of a change, but you never know. It might be the ideal value for that hyperparameter if you're working with a bunch of other hyperparameters, because most of the time you aren't working with just one or two hyperparameters, you have hundreds of them. So any value that you can change that gives you better performance is a good thing. And one thing I do want to emphasize, because I know sometimes it gets a little unclear if you're new to the field, that hyperparameters are different from what we get after we train our model. But remember, hyperparameters cannot be directly trained from the data. We can't say that, oh, our algorithm gave us these values for the hyperparameters. You probably can if you get into some really fancy statistical stuff, but for regular practical ML engineering, you're not going to get your hyperparameters from your data. It's almost the other way around. So you need the hyperparameters to do training with your data. That means you have to have them beforehand. Okay, so now let's talk about DVC briefly. So it did something weird with my little thing down there, but that's fine. So what DVC does, it tracks your code hyperparameters and data changes. It sounds super similar to MLflow, but the difference is that with DVC, you don't have to call an API every time you want to handle a change. And it lumps all three of these things together. So DVC is built as an extension to Git. That means all of your tracking lives in your Git repo. So whether you're using GitHub, GitLab, Bitbucket, whatever, it doesn't matter as long as you're using Git. DVC has these custom Git refs that hold the metadata for all of your code, hyperparameters, and data changes for every experiment you run. So let's say, for example, you're doing some kind of ML project, and today you want to be super ambitious, so you run 100 experiments, which would be incredible. But now you have all of these experiments, and you remember there was one somewhere around number 34 that had really, really good accuracy. The loss was really low, and the training time was short. But now you have no idea how to go back and find that particular experiment. You don't know what code changes were there. You don't know what hyperparameters you used. You don't know what data was there. And it was training epic number 34 out of 100. It's going to take some time to figure out what you did to get those good results. But with DVC, it doesn't matter how many experiments you run because it's tracking all of them. So if you did run 100 experiments today, you could go back to any of them at any point and resume training from that particular experiment. So that is kind of the big benefit of DVC. It doesn't matter how many training runs that you need to do. It doesn't matter how complicated your pipeline might be. Everything you do is reproducible. So in the case of our scenario where we're going through and tuning these hyperparameters, maybe you have 100 different hyperparameters that you're trying to find optimal values for. It's going to take a lot of experimentation to figure out which one of those, well, what set of those hyperparameters actually affect the model significantly. It could take you as an individual engineer months, weeks if we're lucky. But when you have reproducibility, you can split that load across your whole team. So instead of worrying about, well, I already tried this set of hyperparameter values, let me make sure that I have this list of these 100+ values that I've iterated through all day. Let me make sure I just zip all of this up in a file and send it to my coworkers. That's not good. So when we're working with these hyperparameter tuning issues, with DVC tracking everything, it means that everybody on your team can actually run experiments on the same model at the same time, using the same data, the same code, and they can make any tweaks that they want to make, and it's all tracked and it's all reproducible. So if somebody on the team finds this great set of hyperparameter values, then they can share the exact experiment they ran with everyone so that you all have a common starting point now. So that's the cool thing that I personally like about DVC. And something else, it doesn't make you add libraries to your code. So first off, it's code agnostic. So you can use any language you want, whether that's Python, R. We've had some people use Julia, which is interesting to me, even JavaScript. It doesn't matter, DVC does not need to be directly in your code. And then if you get fancy and you want to offload these experiments to the cloud, you can use CML to run those jobs for you. So let's say that you know for sure your training needs to happen on a GPU. You don't want the issue where you're changing not just code, data, and hyperparameters, but also environments. So when you add CML to the mix with DVC, you're tracking everything. So if somebody needed to reproduce an experiment in AWS, they'll be able to do that pretty easily. But that is the reason we're going to be looking at DVC today. No matter how many experiments you run, you can share them across your whole team, and each one of them is reproducible. So with that being said, now we know how we plan on kind of approaching our hyperparameter tuning problem. We're going to use DVC to make sure that we can reproduce everything, because good models are hard to come by, and sometimes they pop up when we least expect it. So the first way that a lot of data scientists or machine learning engineers approach hyperparameter tuning is with a very simple grid search. So a grid search is where you take a set of values for each hyperparameter. So let's say for each of those 100 hyperparameters, they all have 10 values apiece. That means grid search is going to iterate through every combination of those hyperparameters possible. It's going to search over everything. You will not miss one combination of those values. But the downside to this is that that takes a really long time, and it can be super resource intensive. But when you are performing a grid search, if you do have a really reasonable set of values, you'll find the best optimum for those values with the grid search. So that's just a quick intro to what grid search is. And now I want to see if I can switch and share some code with you, because we're going to do a live grid search with DVC right here. This is always the fun part, because I checked this about 15 minutes before this started. So everything was working then. It should still be working now, but let's see how that goes. So first thing I want to do is give you a quick intro to this project. So what we're doing in this project is just a really simple MNIST problem, nothing too crazy here. We're just classifying some stuff. But this is a regular ML project. There's nothing too crazy in here. We have an evaluate script, we have some featurization going on, prepping some data, all of that good stuff. And you'll notice we have this script in here for our grid search. But I just wanted to give you that quick rundown. Now, I want to show you kind of how DVC is added to this project, because we've been doing all this talk about reproducibility and sharing experiments. How does that actually happen? So what we have is DVC's already been initialized in this project. So it's doing its thing in the background and tracking all of our changes. But what it does is, as we run experiments, it adds things to the cache. And the cache is how DVC keeps track of the changes associated with each experiment. So that's a quick background on what's happening as we go through running our training sets. And then one other thing, very important to note, is that DVC is basically a tool that lets us do MLOps. And with MLOps, we set up a pipeline to handle all of our machine learning processes. So with DVC, it handles that with stages. And here it's just, you see, we prepare our data, we featurize it, we run a training set, and then we evaluate how good it did. Like, how good is our model? So we have all of that running, and let me show you what that looks like. I think it's this. So yeah, you get this nice little graphic of what the pipeline actually looks like. So this is the DAG that we're working with right now. We get the data, we prepare it, featureize it, we do some training, maybe you want to do something else over here, and then we do our evaluation. So this is the DAG that we're working with inside of DVC. And the way that we make these stages, you can make it directly just through text here, or there's some commands you can run with DVC that generates this file for you. But the main things that I want to focus on today are going to be in our train and evaluate stages. So in our train stage, you see the script that we're dependent on, the dependencies we have for this particular stage in our pipeline, and you see some params. So these params here are actually our hyperparameters for the model that we're trying to optimize. And you'll notice that it's in this dot notation, and that's because over here in the params.yaml, we have different hyperparameters for different stages. In this case, we're going to ignore the top two, and we just have these hyperparameters for our train stage. So what that means is instead of having all of these hyperparameters in some huge config file that takes forever to figure out how to edit, and then you have to commit every change that you make to the hyperparameters. And if you don't use Git to track it, you have to do a whole separate zip file with your model and your data and the hyperparameters. We don't have to do all of that with DVC. You have your params.yaml. It has all of the hyperparameters you need divided up by stages. And you have your dvc.yaml, which has all of the stages in your pipeline. So whenever we change a parameter here, it's going to execute this train stage and this evaluate stage. So at the end of our training, we have this model that's outputted, and then we go ahead and evaluate that model in the evaluate stage. This is where we'll get all of our metrics to compare how well each training run did with each other. So we got some metrics to look at, and we got some plots. So I think that's a pretty good background for DVC right now. So the way that DVC works, if I come over here, actually, let me leave that params file open. If I come over here and we look at our grid search, so it's a very small script. And basically what we're doing, we are taking these two hyperparameter values, and like we mentioned earlier, we're giving each hyperparameter a set of values we think will be good. So just to make sure I don't get any weird data conflicts, I'm gonna use some numbers I haven't used before. Let's do 190. Yeah, these are definitely good values, right? I'm sure they're going to be fine. But anyways, we have our set of values for each hyperparameter. And what we're going to do now is actually take advantage of something DVC does for us. So with the DVC, let's say you are doing a hyperparameter search and you have way more hyperparameters and sets of values for each of them than this. You probably don't want to sit there and execute that training step manually for every combination of hyperparameter values. So you can automate it. And that's exactly what we're doing here. So what we're doing is setting up a queue of experiments with different values for each of the hyperparameters. So just gonna run the command. Well, I'm gonna run this script just so that y'all can see how that works. So we have this grid script running, and all it's doing is this sub process in the background where it executes this DVC exp run for the combinations of hyperparameters. Now we have 4 experiments that are in our queue. So if we take a look at this table, I'm going to turn the timestamps off because it's just easier to see. Oh, maybe I typed in the wrong, there's no timestamp. There we go. So now we have this table with those 4 experiments queued up. And if we tab over a little, you can see the different hyperparameter values here. So actually, I'm going to make this table a little bit cleaner and just include the hyperparameters that we're tuning. So we got our min split. Okay, that's a lot easier to read. And what you see, we have those 4 experiments that were queued up from the grid search. You can take a look at those hyperparameter value combinations before you run the experiments, because if there were any issues that you saw, maybe there's some values that someone else has already tried, or maybe you just see a combination that you kind of recognize from an earlier experiment and you know it's no good. So if you did want to get rid of those queued experiments, you would run dvc exp remove, and then we'll get rid of everything in the queue. And if I look at this table again, you'll see all of those experiments are gone. But that's just one of the ways you can work with experiments here in DVC. And you see how nicely it tracks everything for you. But with that being done, we see all of these experiments queued up. Let's just go ahead and run them. So we're going to do that with DVC exp-run all. All right, so what it's going to do right now is go through all of these experiments. And as it's going through these experiments, it is executing this train and this evaluate stage, because these are the ones that have changes we've noticed. This is something else cool that DVC does. So instead of having to start your pipeline completely from the beginning, and you have to re-download the data, re-featurize it, if there aren't any changes in your data, it's not gonna go all the way back. It's just gonna start from where it senses the changes, which in our case is the train stage, because we updated these hyperparameters, which gives us a new model that we then need to evaluate. So let's see how we're doing. That finished faster than I expected, which is always so great. So what we have now, we've run 4 experiments with this grid search. Let's take a look at that table. And isn't it beautiful? You see how we have the executed experiments. There is the average precision and the ROC AUC curve value associated with them. And we can see how those values tie to each set of hyperparameter values. So if I wanted to, we see that the last experiment we ran compared to the other ones didn't do that great. And we also see that it looks like the first experiment we ran did really, really well. That means we probably want to resume training with these 2 hyperparameter values, because it's something about that combination that gives us a better average precision. So this is what I mean when I say our experiments are being tracked. So all of these experiments, you see they have the associated IDs. It means that there's metadata attached to those IDs that has a connection to these specific hyperparameter values, our code, and our data. So if you wanted to go back and reproduce any of these experiments at any time, you can, just because DVC has the exact changes associated with the experiments based on these ID numbers. And if you were working in, a group of engineers, you could actually share these experiments with them. So let's say you and your team have been working on this model for months, and this 5.6 is the best average precision you've ever seen, which is great. And now you have the exact combination of things that made this model. So you have the model weights, you have the code, you have hyperparams, you have everything you need to pass this to another ML engineer so that they can get these exact same results, which this might be a little side note, but this will help a lot in academia for those papers with those really good algorithms, because it's so hard to reproduce those sometimes. But I digress. I just want to make sure that you see, even with this grid search, we are able to track everything. And of course, that would be more impressive looking if we had hundreds of experiments here. But I hope that this drives home the point that no matter how many of these experiments you run, DVC is tracking the changes for all of them, and you can go back to any of them at any time. So we've run a grid search now. It's great, right? We got to try out all these different values, and it really didn't take us that long at all. So now let's go ahead and go back to the presentation where we talk about random search. So random search is another approach that ML engineers take to tuning hyperparameters, but it does take considerably less time than an exhaustive grid search. So with the random search, it's just gonna hop around the values that you give it. So if you do have 100 hyperparameters, each of them have 10 values each, it's not gonna go through every possible combination of those values. It's just gonna hop around all of those values and give you almost a random sampling of what combinations you can get from those values. And a lot of times, if you run a random search for the same amount of time as a grid search, you'll likely converge on an optimum faster just because you get a wider range of values. So again, this is a great time to have reproducibility, because if you're running a random search, you don't necessarily know which values are associated with an experiment. So you could get some kind of crazy average precision that's like 77%, and you got it from your random search, but you have no clue which combination of those values actually did it. So for our little toy examples, it looks super easy to be like, oh, it was just one of these 2 sets of combos. But when you have that 100 hyperparameter with the 10 values each, it's not that easy to go back and figure out what exactly you did to get such a good model. That's why we have to use these MLOps tools to give us the ability to go back at any point. It's going to save us a lot of time, a lot of frustration, and a lot of resources of rerunning the same experiments, hoping that you get that same value again. So now that we've talked about random search a bit, let's jump back into some code and see how to do that with DVC. So you've already seen our grid search, so I'll go ahead and close that. Now, random search is going to be super similar. In this case, we had 4, We have 4 different combinations for our grid search. So I'm going to go ahead and do 4 experiments for our random search. And then I'm going to take this same range of values for each hyperparameter. That way, we're just working with the same thing, and you can kind of see how random search and grid search compare. So we have these same values. I think I'll reverse the order just because it feels right. All right, so what we've done here is pretty much made our random search use the same set of values as the grid search. That way it doesn't have some kind of unfair advantage or disadvantage in the starting point, and we can see just how well random search does. So I'm gonna do something similar. I'll clear out my terminal and we'll execute this random search script. So I'll run this. And this is gonna queue up those 4 experiments for us. So what's happening, again, we're running this queue command with random values for each hyperparameter. And before we run the experiments, let's just take a look at that table because I'm curious what values it gave us. Okay. These are completely different from what we had in our grid search by leaps and bounds. And right now we have no idea whether any of these values will be better than this result we got with our grid search. So you might have somebody on the team that maybe argues, oh, we need to try more values for the min split. That's the one that really drives the difference in our model's performance. And then you might be the one that found this really great experiment and you believe it's the NEST value that makes a huge difference. So this is where grid search might come in and help tune your tuning. But basically, we have some more experiments to run, so I will go ahead and execute all of those. And that's something else I kind of want to mention. So when we queue these experiments, you don't necessarily have to run them on your computer. You can offload this stuff to the cloud and just let your queues go crazy. So if you do have a lot of computing resources, or you know you need access to a GPU, or you know you just need to run thousands of experiments to get a good model, this is the start of an approach for that. So even when you upload your training to the cloud, DVC still tracks all of those metrics and changes in the background. So no matter where you run these experiments, you don't have to worry about that issue of reproducing the results. If you did find, like maybe you have some metric threshold, like there's a certain accuracy that you're targeting and you set a monitor for that in the cloud. And whenever that metric is encountered, the cloud lets you know, hey, this is the experiment ID that gives you the model that you want. You can then take that experiment ID, pull that particular experiment down to your machine or anybody else's machine, and it has the exact data, code, hyperparameters, and even the environment that this training was running so that you can reproduce this model and make any updates. You can do a lot of testing before it goes to production. You can send it to someone to see if find something better. It's just easy to share these results when you have all of the work that went into each experiment. It's just convenient. So now that we have all of the random experiments run, I'm gonna clear the terminal and let's see which did better. Okay, so this is everything, including the new experiments. So if we look at our random search, wow, it looks like grid search actually did better than random search this time. And that's not too surprising because we only ran 4 experiments for each. But it does kind of give you an idea of which direction to go. Maybe. At least you know what your best experiment is now. So this could give you a baseline to start maybe trying a different algorithm if this isn't getting you the accuracy that you need in the amount of time that you have. Is just a lot of different things you can do at this point. So for example, let's say you wanted to compare 2 different experiments. So we'll take a look at our best experiment ever, and then we'll take a look at the best that the random search gave us. So I have those 2 IDs in here, and you see it gives you just this quick little snapshot of the difference. So the first experiment we put in is the first value you see, and same with the second. So what we have the first time is that our, where is it? The average precision between these experiments has this kind of change. So that means that the first experiment is better because we have a negative change here. Same with the rock AUC value. And then down here, you can see the difference between the hyperparameters, like how much bigger or smaller were those hyperparameters. And then if we want to take a look at some plots, let's check out the difference between these 2 experiments. So we have that first one. Let's look at a few of them. So I'm going to take the best and the worst ones, and we will look at a plot of them. So let me get that. All right, it looks like it made our plot file. So if I come back here, actually, let me see something real quick. Okay, so just want to make sure I'm sharing the right screen. So you should see these graphs now. And what this is just a plot comparison of those different experiments metrics visually. That's it. So we have these 3 different experiments. I'll zoom in a little bit just so you can see the colors better. But you'll see these 3 different experiments here by the IDs, they're color coded, all that good stuff. And it's easy to tell which one is probably the best. So I'm going to go out on a limb and say it's probably the blue one. Maybe the orange one's okay. It just depends on what you're looking for. But you get these plots, they're automatically generated by DVC so that you don't have to worry about going through your metrics and making them look pretty when you present to people. But this is a great time to switch back to the slides because it's time to wrap up. So hopefully you saw how useful reproducibility and sharing experiments can be, especially when you're working on some really complex model, because all of them are actually really complex models, and going through hundreds of training stages and working across teams with multiple ML engineers, it makes it hard to keep track of where the best model came from. Maybe you did get the best model and all of you are in agreement, but when you go to deploy it to production, there's some other issue because something just wasn't tracked. But with DVC, you don't really have to worry about that as much. It takes the concept of doing deploys, like when you're working with a web app or something, you can go back to any previous model that you've created at any point. And with that being said, let me just wrap up. So tuning your hyperparameters quickly will make your model better a lot faster. And that's just because when you're able to reproduce experiments, you don't have to keep going over the same values multiple times. You do it once, you don't have to worry about it because you can go back later. And then next thing, DVC and CML help you tune hyperparameters and version your data and keep your experiments reproducible across pretty much any environment. And lastly, my favorite, don't be afraid to try new tools. There are a lot of hard problems out here for machine learning engineers. You don't need to make your own tooling on top of making the models, on top of handling the data engineering, on top of all the other stuff that we have to do. That is why it's okay to try new tools. So honestly, if you do use MLflow, I challenge you to check out DVC and see if it's something that might fit your needs. But with that being said, I'm going to wrap up. My name is Milecia McGregor, and you can always reach out to me on Twitter at FlipCoding. But I am here to take questions now if y'all have them.